We can now find the solution of a discrete dynamical system if A is D, if A is PD, P inverse, and if A is C. You may wonder about the last case. What happens if A is B, C, P inverse? We can do this case too. It is sort of a combination what we did in the PD, P inverse case and the C case. So we have all the ingredients, and let's put them together. So we have our discrete dynamical system, xk plus 1 equals A times xk. We have A equals PCP inverse. And then we know from the PDP inverse case what to do. We put yk equals P inverse times xk. That yields yk plus 1 equals P inverse times xk plus 1. We know xk plus 1 equals A times xk. So we substitute that and use A equals PCP inverse. Then the P inverse and P cancel out here. We have a C left and a P inverse times xk, which yields a yk. So we find C times yk. So the y problem is just a problem yk plus 1 equals C times yk, a problem we have already solved. So let's do an example to solve the full problem. Suppose we have a matrix A over here. As you see, it's not a scaling rotation matrix yet, but if you compute the eigenvalues, those are 0.9 plus 0.2i and 0.9 minus 0.2i, we see that A has complex eigenvalues which are each other's complex conjugate. Check this yourself. Then we have the eigenvectors corresponding to lambda 1 and v1, 1 minus 2i, 1 and 1 plus 2i, 1. So there we have all information of the matrix A. And now we know that A is similar to matrix C. We know A equals PCP inverse with P and C over here. If we pick lambda 1 equals 0.9 plus 0.2i, and here I have to put the A's, so the 0.9, B equals 0.2, so the B and the minus B over there. That yields our C matrix. For our P matrix, we need to take the real part of the eigenvector in the first column, so 1, 1, and minus the imaginary part, the minus sign, as a second column. Imaginary part equals minus 2, 0, so minus the imaginary part equals 2, 0 as a second column. And then first we sketch the phase space in the yk language. I have our C matrix here. We have yk plus 1 equals C times yk. We see that the R is smaller than 1 and the phi is bigger than 0. The R smaller than 1 means we are circling inwards, and the phi bigger than 0 means we are circling towards the left, that we are circling counterclockwise. So we have here a stable spiral point. Well, how does this look in the X language? We take the V1 and V2, the V1 over here in bluish color and the V2 over there. Suppose we start over here on the V1 axis, so this point over here corresponds with that point over here. We circle towards the V2 axis, so we circle towards the V2 axis, the positive V2 axis, then we continue towards the negative V1 axis, so we continue towards the negative V1 axis, then we continue towards the negative V2 axis over here, so the V2 axis over here, so we continue towards the negative V2 axis, etc., etc. So as you see, here we are circling counterclockwise, but due to the axis we are circling here clockwise. So always check towards which direction you are circling. So here we have our phase space in the xk language. Well, we can write down the solution explicitly for xk, because xk equals p times yk. So we get a p yk equals c to the power k times y naught equals p inverse x naught. So okay, over here we have our solution explicitly, but usually a phase diagram like this one over here is much more information of how the dynamical system behaves. So always make the phase space plot.